Let us start this lecture with a thought process by Albert Einstein, who says education is not the learning of facts, but the training of minds to think. Unfortunately, modern education is not providing an opportunity to develop a good mind, rather it is emphasizing on learning of facts. So, let us recall what we learnt in the last lecture. In the last lecture, we basically looked at how does the lifetime of a fuel particle varies, and we also looked at the time requirement for initial droplet diameter burning for carbon and kerosene, and then we also discuss about the coal sphere and being a volatilized or pyrolyzed fuel sphere. And later on we moved into the temperature to derive expression for the temperature profile, and we had derived the expression for temperature in between. That expression is basically, let me write down again, that is R square C P T is equal to kg R square dt by dr plus S R square delta S C. Keep in mind this we had given equation 4, if I remember correctly. And if you look at these remain constant, right, by continuity we know that m dot double dash r square is equal to nothing but your m dot s r square. So, we can write down here basically in this place I can write down m dot s r square, right, remains same. So, by rearranging equation 4, we can write down, we can have, that is m double dot s r square, and I can take this C P T and then minus delta S C is equal to kg r square. I can write down dt by dr, Cpt, Cp I can minus delta Sc. So, if you look at, so I can write down basically Cpt here 1 by Cp here. Now, I can simplify further. It further, we can have d Cpt minus delta Sc divided by Cpt minus delta Sc I can have is equal to r square dr by r square I can write down, and this is kg by Cp. and now I can integrate it this one from t to t infinity, and similarly here I can integrate with respect to basically r to r is equal to infinity. And keep in mind that we can simplify here kg by rho Cp, I can write down basically alpha g is nothing but your kg by rho Cp, and this is your thermal So, we will get by integrating this is basically ln Cp T minus delta Sc is equal to and I can write down kg by Cp is nothing but your alpha g by rho g, I can say this is rho g, and minus 1 by r and this integration from r to infinity. And that is equal to, if you look at when r is equal to infinity, that will be 0. So, this become basically I can is nothing but your s r square r s square divided by alpha g by rho g 1 by r. So, this is basically I can say equation 5, and we had earlier derived an expression for similar term in terms of mass fraction of oxidizer. So, as we had derived an expression for this term like as m dot s r square by rho g diffusivity 1 by r is equal to ln y o x this is basically t to t infinity y o x infinity plus 1 by f y o x plus 1 by f. Let us say this by combining this equation, and also we can write down equation 5 and 6 we can have. Keep in mind that this when we will integrate this term, I will get basically ln Cp T infinity minus delta Sc Cpt minus delta Sc, and this term will come. So, which is nothing but your equal to, in place of this I will be replacing this, I will get is equal to rho d 1 by 2 rho g divided by rho z alpha z is into ln y o x infinity plus 1 by f y o x plus 1 by f. So, this will cancel it out, I can say this is equation 7. Now, we got an expression basically in terms of temperature and also the mass fraction of oxidizer. Now, if I take this anti-log and keeping in mind that Lewis number is equal to 1, in this expression Lewis number is equal to 1, we have considered Lewis number equal. That means, the basically diffusivity is nothing but your alpha g, that means this is going to 1. So, therefore, we can simplify this equation 7 and also taking anti-log by simplifying equation 7 anti-log, we can have CPT delta SC, CPT infinity delta SC is equal to YOX F plus 1 divided by YOX infinity F plus 1. We had derived earlier that YOX A plus 1 YOX infinity A plus 1 is nothing but your BC plus 1 power to the R by R. So, this is your basically 8, I can say this is 9. By combining equation 8 and 9, we can have CPT delta SC, CPT infinity delta SC is equal to BC plus 1 R by R. So, if I this is my equation 10, if I simplify further, I can get an expression for Cp for temperature Cpt is equal to delta SC plus Cpt infinity minus delta SC Bc plus 1 R by R, and we can basically simplify it further and get some expression like that. That is, I will get, because if I divide this by the Cp, this equation Cp here, Cp here, similarly Cp with this, I will get T is equal to delta SC by Cp is equal to T infinity minus delta SC by Cp Bc plus 1 R minus R. So, this is the expression, it is 11. Now, if you consider this at the fuel surface, T is basically T s, and fuel surface means what? R by R equal to 1, and B c is, we know, that is F y o x infinity, and equation becomes T s is nothing but your delta S c C p and plus T infinity delta S c by C p. I can write down here that in place of B c I can write down F y o x infinity plus 1, and this will be minus 1. And if I will simplify this expression, I will get T s is equal to, basically I can do that I will get, I will just write down the final expression, that is T infinity plus F delta S c y o x infinity divided by C p F y o x infinity plus 1. So, this is the expression you will get the surface temperature 12. Now, keep in mind that this expression temperature is varying with respect to radius, and of course, it is a function of values, like for example, T is a function of what? T is a function of delta S c, also function of F, sorry, T s is a function of the F and delta S c, and also the T infinity and y o x infinity, and these properties basically combustion parameter. And these are ambient conditions. So, by that means T s is basically function of F and also delta S c, and it will be dependent also the T infinity and y o x. F is basically fuel and oxidizer ratio. For example, if we will consider the carbon sphere is burning in the presence of air, and to produce carbon monoxide at a moderate temperature and with deficient oxygen level. So, as per the reaction, it will be 2 C plus O2, it is going to basically 2 CO2. And in this case, the what will be F? F will be basically 24 by 32. And if I consider T infinity is 300 Kelvin and y o x infinity will be 0.232, and if I consider the heat of combustion as 8.4 megajoule per kg and C p value I need. So, C p I will take 1.148 kilojoule per kg Kelvin, I will get a surface temperature which is 1340 K. And I can consider another extreme situation where the large quantity of oxygen is diffusing to the carbon particle, right, oxygen is diffusing large quantity, is not deficient and it is at high temperature, right, then we will consider basically the reaction to occur at high temperature and excess or oxygen level. So, we will say that the reaction which will be occurring is C plus oxygen going to the carbon dioxide. In this case, F will be 12 by 32 and we will take the same condition, T infinity is 300 Kelvin, YOX infinity is 0.232, but however, delta SC may be higher. So, we will consider as 30.5 megajoule per kg. If I substitute all these values in equation for the surface temperature that we had derived earlier, we will get the Ts is 2402 Kelvin, right. We will evaluate that and keep in mind that this is a we have estimated from this analysis. However, the actual temperature if we will measure, it will be much lower as compared to this estimated surface temperature of carbon sphere. A question arises why it is so. It is because of fact that we have not considered the radiation losses from the fuel surface, which is quite exorbitant, and also the properties which we have taken as a constant. So, therefore, basically temperature will be much lower. So, let us look at how does this temperature varies in the gas phase for this CO case. So, it will be decreasing with respect to R and this is your basically fuel surface. This is corresponding to R by R equal to 1 and this is the fuel surface, right, at fuel surface this point. So, it is decreasing, asymptotically decreasing and we can see that. Now, we have looked at this on the quiescent atmosphere, but let us look at what happens when it is in a convective atmosphere, like means carbon sphere in convective environment. See, if you look at in real situation, what happened, it is not that we will have to burn the any fuel sphere or fuel particle in a quiescent atmosphere, but mostly with the flow. So, if I assume there is a flow which is taking place, let us say this is a uniform flow with a V, then what will happen? There will be some boundary layer will be formed, right. This is your boundary layer and also the flow will be slightly separated out and there will be wake formations, wake region, because this is the point of flow separation. And of course, for this you want to analyze, it is quite difficult and you will have to basically solve the momentum equation and 2 dimensional at least or maybe 3 dimensional, it is quite complex and which is difficult to tractable along with the chemical reaction. Therefore, people have conducted experiment and they have come up with a basically empirical result and the experimental results for heat transfer coefficient. What is more important, the how much heat being transferred from here. If we evaluate, then we can also find out what is the droplet burnings and other things. So, we can do that result for the convective heat transfer coefficient H as H by Cpg. This is basically gas is equal to rho g diffusivity, and d naught is the initial droplet diameter 2 plus 0.6 RE d. This is half and this is 1 by third Schmidt number. So, d is basically initial diameter of fuel, and Cpg is specific heat of gas, and if you look at Reynolds number is based on diameter. This could have been d, okay, diameter d naught I can write down rho v d naught by mu. This is your Reynolds number, and Schmidt number is nothing but your kinematic viscosity divided by diffusivity, and v is basically one can consider the actual velocity, or in real situation you can consider the relative velocity between the sphere and fluid, because this particle also will be moving. So, therefore, it is important to take the relative velocity, and keep in mind that you will, by using this expression, one can get a similar to the d square law. It is not d square law, but you can get some expression. By that you can really use it in a actual calculation. So, with this we will stop over, and in the next lecture we will be moving into a new topic, combustion and environment. Thank you very much.